Hello class, this chapter is on the electronic structure of atoms and quantum theory. First we have to talk about the electromagnetic spectrum, or what we usually call light. Shown in the diagram on the right is a representation of a sinusoidal wave, which is described by the following characteristics or parameters. One parameter is a wavelength, which we usually abbreviate as lambda, which is the distance from the peak to peak, or the point at which it crosses the sort of midpoint here. So this would be one wavelength, or this would be one wavelength. The frequency is the number of wave crests or wave forms per second, and it's given in units of reciprocal seconds or hertz, Hz. The period is a time in seconds between the crests, so it's essentially the reciprocal of the frequency, so you either deal with the frequency or with the period. The amplitude is the peak to peak, or sometimes it's from the midpoint to the peak, and either one would be useful in determining the amplitude. And then we have the velocity, the linear velocity of the wave. Now, if the wave is electromagnetic radiation or light, it travels through a vacuum with a speed of 3.0 times 10 to the 8th meters per second. Light travels a little more slowly through other media, such as glass or water. But through a vacuum, the speed is 3 times 10 to the 8th, and it's only slightly slower in air. So we usually use the number 3 times 10 to the 8th. We see in the right the formula that the velocity, which is the speed of light, is equal to the frequency nu times the wavelength. So the product of the frequency times the wavelength is this constant called the speed of light. And we'll see the consequences of that when we talk about different regions of the spectrum. Another important equation is that the energy of light is equal to a constant, which we call Planck's constant, times the frequency, or in other words, energy is directly proportional to frequency. This proportionality constant, called Planck's constant, is a very, very small number, 6.626 times 10 to the minus 34th joules seconds. So a very, very small number. Now we can also express this equation as energy is equal to Planck's constant times the speed of light divided by lambda, because the speed of light divided by lambda is the same thing as nu, as you can see from simply rearranging this equation. This shows the electromagnetic spectrum of light going from the short wavelength, high frequency region of the spectrum to the long wavelength, low frequency region of the electromagnetic spectrum. All of this is electromagnetic radiation. At the high frequency, short wavelength side, we have what we call gamma rays and X-rays, and then on to ultraviolet. These are extremely short wavelengths, 10 to the minus 5th nanometer, or nanometers, 10 to the minus 9th meter. So this is a very, very, very short wavelength and a very, very high frequency, 10 to the 24th. On the other end of the spectrum, we have radio waves and then microwaves. Radio waves can be a mile long, 10 to the 3rd meters or a kilometer, and they have very low frequency, 10 to the 2nd hertz. Now, you'll notice, as we had from the previous slide, that the product of the wavelength, lambda, times the frequency is a constant. So when one becomes a larger value for the wavelength, then the frequency becomes smaller. Likewise, when the wavelength becomes shorter, the frequency becomes higher. Now, in the middle of this region, we have the visible region, which is surrounded by the ultraviolet and the infrared, two other regions of the spectrum you probably have heard of. The visible region, if we blow it up, we see that it exists between about 430 nanometers to about 750 nanometers. 430 would correspond to blue light, 750 would correspond to red light, and we have yellow, which is approximately in the middle, about 580 nanometers. So this is the electromagnetic spectrum. If you recall from the previous slide, where energy is equal to this proportionality constant, Planck's constant, times nu, then the high energy region of the spectrum is in the gamma X-ray region, and the low energy region is to the right, to the long wavelength radio waves. Another feature that we need to mention is the existence of standing waves. If you look at the bottom left, you see where an experimenter is taking a rope and is whipping the rope back and forth and is forming standing waves, where we have a node that can be formed in the middle. Of course, the nodes are on either end, but also if you have at enough energy, you can form a node in the middle or even two nodes in the middle. Now, the standing wave phenomena will be important, as we'll see shortly, in terms of the possible orbits that electrons can occupy or can travel around the nucleus of an atom. Now let's give a series of important discoveries and concepts that led to the theory of quantum mechanics. And let's begin with Max Planck, a German scientist who studied emission from black body emitters. Black body emitter is essentially if you take a piece of metal and heat it up till it's glowing hot, the light emitted is from what we call a black body emitter. Planck made the revolutionary hypothesis that energy travels, that energy levels in an atom are quantized. That is, an atom gains or loses electrons in multiples of some integer, whole number, integers, where the integers could be numbers like 1, 2, 3, 4, 5. And he came up with the equation that E equals, of course we had E equals h nu, but E equals n times h times nu, where n is this integer, which could be, again, 1, 2, 3, 4, a whole number. And of course, the Planck's constant is named after Max Planck. Again, its value is 6.626 times 10 minus 34 joule seconds. And nu is the lowest frequency of the light that can be absorbed or emitted. That's in that equation. The next important scientist is Albert Einstein, a Swiss scientist who immigrated to the United States. He worked as a patent clerk and made a number of discoveries. One, which is called the photoelectric effect, where photons strike certain metals that can cause an ejection of electron. Now, the reason this is important is because that process of electrons striking a surface and kicking out an electron is more of a particle-like property of light. And so Einstein is credited with coming up with what we call the duality of light, where light can sometimes act as a stream of small particles, which of course we call photons, and other times it exists as a wave, or it has wave properties. So electromagnetic radiation can be considered to be a stream of small packets of energy, massless packets of energy called photons. Another important discovery was the discovery of the line spectra of hydrogen gas. When a container of hydrogen gas is excited with electrical voltage applied across two ends of like a glass tube filled with a gas, it turns out that the gas inside will become excited and will emit light. It will shine, just neon lights. But the light is not a continuum. And in fact, with monochromators or prisms, one can resolve the emitted light into line spectra. And this was an amazing discovery to physicists. As you see at the bottom right hand, we show the line spectrum of hydrogen, showing that there are, in this case, four in the visible region, four discrete lines that are emitted by the glowing hydrogen gas. Now, this was an amazing discovery to scientists, and actually a music teacher, Johann Balmer, came up with an explanation for this, and he says, here's an equation. This is what we would call a phenomenological equation, an equation that describes the behavior, even though we're not quite sure why it describes that behavior, or at least they weren't sure at the time. His equation was that the 1 over the wavelength is equal to some constant, r, and that constant we will call the Rydberg constant. But that constant multiplied by 1/4 minus 1 over n squared, where n is an integer greater than 2, like 3, 4, 5, 6. That if you plug those integers, like 3, 4, 5, into this equation, you can predict the exact wavelengths for the line spectrum of hydrogen gas. Pretty fascinating. Well, then Niels Bohr, a Danish scientist, came up with an explanation for this. He postulated that the line spectrum of hydrogen gas can be explained in terms of electrons occupying certain energy states, with these energy states being quantized. Like standing waves. Remember our standing waves that we had, or the standing waves you could have in a string instrument like a guitar. Only certain standing waves can exist. Well, he postulated that if electrons traveled in an orbit around an atom, maybe they had to form complete waveforms, like one waveform, two waveforms, three waveforms, four waveforms, and that only complete waveforms were allowable, and that there couldn't be fractional waveforms. So he began with more physical principles of motion, and he came up with this equation, that the energy of an electron traveling around a nucleus is equal to a bunch of constants, minus r, that Rydberg constant, which we won't even go into, but it's just a number, times Planck's constant, times the speed of light, divided by n squared. Now, if we multiply r, h, and c together and just come up with a number, anytime you multiply numbers together, you'll get another number. That value of RHC becomes 2.18 times 10 to the minus 18th. So let's just deal with this equation. The energy of an electron in various energy levels described by n values of 1, 2, 3, 4, that is whole numbers, is equal to minus 2.18 times 10 to the minus 18th divided by n squared. So if we plug in n equal 1, squaring it's 1 of course, we would get the energy level for n equals 1. If we plugged in n equals 2, squared it, we would get the energy level for level 2. And we can calculate those. Of course, the easiest one is for n equals 1. If we plug it into the equation, we get the energy for level 1 of an electron traveling around a nucleus of an atom, of a hydrogen atom, would be minus 2.18 times 10 to the minus 18th joules. If we plugged in n equals 2, we would get the energy level for energy level 2, which would be minus 5.45 times 10 to the minus 19th. You can plug these numbers in and see that these are all correct. And this would be the energy for energy level 3 and energy level 4. And what you would see is a pattern in which the energy level 1, or when n equals 1, we're at a lower energy level than when n equals 2, then when n equals 3, and n equals 4, 5, 6, etc. And in fact, they kind of bunch up till you get to n equals infinity. Okay, now the convention of the way we have these so-called energy diagrams is that the lower the value, the more stable the energy level. So the most stable energy level for an electron traveling around a hydrogen atom, the nucleus of a hydrogen atom, is for n equals 1. This would be what we call the ground state, or the lowest energy level state. So, according to Niels Bohr's description, an electron could either travel around a hydrogen atom in the n equals 1, the lowest energy orbit, or n equals 2, a higher energy orbit, n equals 3, even higher energy orbit, or 4, even higher, etc. But now most of the time, the electron is going to travel around the lowest energy orbit because it's so much lower than the higher ones. Okay. Now, remember that Balmer series? Okay. Another equation that we can derive from the one above is that if we have a change in energy levels, if an electron goes up from one energy level, like from energy level 1 to 2, or goes down from like energy level 3 to 2, or up from 2 to 4, that we can calculate the change in energy by using this equation, minus RHC, and again, RHC is just 2.18 times 10 to the minus 18th, minus RHC times the quantity 1 over n final squared minus 1 over n initial squared. Okay, so this is how we can calculate the energy steps in going either up or down. And it turns out if we go up, the value of delta E will be positive. If we go down, the value of delta E will be negative. And later on, we'll talk about endothermic and exothermic reactions, and this will make more sense then. But back to that Balmer series, the visible spectrum of the line spectrum of hydrogen. It turned out that the wavelengths that we see are from transitions going from energy level 3 to 2, energy level 4 to 2, energy level 5 to 2, and 6 to 2, and that these are actually the transitions that result in the line spectrum of hydrogen gas. And the reason we don't see other transitions like 2 to 1 or 3 to 1 is that these are outside the visible spectrum range, so we just don't see them. Oh, I just noticed that Niels Bohr has a striking resemblance to this famous baseball pitcher, Bob Feller. I don't suppose they were the same person. They lived at about the same time, though. Okay, some other important scientists and other aspects about electrons and their properties. Louis de Broglie speculated that if photons can have dual properties of being particle-like and wave-like, as Einstein had posited, why can't electrons also have dual properties? They're small as well. They're not, of course, they're not massless as a photon is, but they're small. And so he developed an equation called the de Broglie equation, or the de Broglie wavelength, which is given here, which says that small things that move very rapidly, can act as if they have a wavelength equal to Planck's constant divided by their momentum, mass times velocity, where lambda is the de Broglie wavelength for a particle like an electron, with mass m and velocity v. Essentially, this equation says that things that are very small and that move very rapidly, of course, photons have no mass, so they're the smallest, but if you have small things like electrons moving very rapidly, they can behave as if they have a wavelength, and therefore they can have wave properties. Conversely, large, slow-moving things like us have a much smaller wavelength and do not even act as if we have wave properties. Now, knuckleball pitchers and baseballs that are thrown, sometimes, I don't know, maybe there's exceptions to those and they can have wave properties. Okay, another property is that a stream of electrons will diffract when passed through a narrow slits, as do photons, which is evidence that electrons, just like photons, electrons can have wave-like properties. All right. Werner Heisenberg then proposed an explanation to explain a lot of these aspects of the behavior of electrons in terms of what he called the uncertainty principle, which is given by this other equation on the page, which is delta x, which is the uncertainty in determining the position x along some Cartesian coordinate, let's say, and the uncertainty in determining the momentum, mass times velocity, of a fast-moving particle like an electron is greater than this small number called Planck's constant. Now, what this equation means is that the uncertainty in the position of a small particle, such as an electron, times the uncertainty of its momentum is extremely small, or in other words, fast-moving small things cannot simultaneously determine their position and their velocity. Sometimes this is explained that is, if you try to determine the position of a fast-moving object, you will disturb its velocity, or if you try to determine its velocity, you will disturb its position when it's very, very small and moving rapidly. Another way of thinking about this is that small, fast-moving things are fuzzy. Now, with that as a backdrop, then two research groups, one led by Niels Bohr from Denmark and the other led by Erwin Schrödinger in Austria and then in Germany, attempted to further describe the motion of electrons in an atom, leading to this theory of quantum mechanics. Now, Schrödinger derived a complete equation for the motion of an electron in the hydrogen atom. It's called the Schrödinger equation. It's one of the most famous equations. You'll sometimes see t-shirts, and you have to be a large person to have all of the equation on your t-shirt because it's a very large equation. It includes the concept of a wave function psi. That's not a pitchfork. That's not a sloppily written 4. That is a Greek letter psi, and if you go to this university, you have to know your Greek letters. So psi is a mathematical function that describes a probable location of an electron around a nucleus, and it has the following characteristics. 1. Only certain wave functions are allowable, corresponding to n values, integer values of n, like 1, 2, 3, 4, the same type of n value as in the Bohr equation. In other words, electrons are quantized. The square of psi, the square of this wave function, at any point from the nucleus in like a Cartesian coordinate, x, y, z, gives the probability of finding an electron at that position from the nucleus. The probability, that is, 20% or 5% or 1% of finding at that particular distance. Or in other words, it doesn't completely localize it, but just gives the location in terms of chances or probability. And that's consistent with the Heisenberg principle that you can't tell exactly where a fast-moving small particle like an electron is. Also, the Schrödinger equation predicts orbitals, that is almost like racetracks of electrons around a nucleus, the shapes of these orbitals, their directions in space. And it does so in terms of 3 principal quantum numbers, which we're going to talk about in the next slide. These are N, L, and ML. You ready? N is called the principal quantum number, and it has integer values again. Again, this is the same kind of N as in the Bohr equation. Values of 1, 2, 3, 4, etc. And it determines the energy level of electron. Remember, n equals 1 would be the lowest energy level. Then we'd have 2 and 3, 4, 5. The smaller the n corresponds to lower energy, more stable electrons. When n equals 1, we're in the ground state. Now, the n values can also be referred to as electron shell levels. Sometimes we will talk about the first shell and the second shell and the third shell in terms of n equals 1, 2, and 3. L is called the angular momentum quantum number. And it has values of 0, integers. It's also integers, but it is a value 1 less than the n value, or up to 1 less than the n value. So if n equals 1, the only possible value of L is 1 less than 1, 0. If n equals 2, the possible values of L are 0 and 1. If n equals 3, the possible values of L, 0, 1, and 2. That is, it can be any value up to 1 minus what the n value is. And it's a little bit difficult, but as we go, you'll catch on to this. The L values indicate subshell orbital types, which have different shapes and orientations in space. Okay. Now, I have a little table which tries to summarize this. And again, I know the first time you see this, it looks like Lost in Space. I understand, but it'll get easier. And it'll get easier, especially if you look at my second column where I have subshell labels and I use different symbols, because some of the problem with this is that we reuse numbers. We use integer values for n, we use integer values for L, and it can get a little confusing. Okay, so quickly in your mind, if an L value is 0, we're going to call it, most of the time, we're going to call it an s orbital. So over to the left, when L equals 0, we're going to call it an s orbital. When L equals 1, we're going to call it a p orbital. L equals 2, a d orbital. 3, an f. 4, a g. And if you make that substitution or correlation in your mind, it'll keep you grounded a whole lot better. Now, the s orbitals are spherical orbitals. We'll show pictures of them in a second. There's only one type of s orbital per energy level, so we just call it s. When L equals 1, we have what is called a p-type orbital, which sometimes we describe it as a dumbbell shape, and we'll show this in the next slide. There can be 3 p orbitals. We call them px, py, pz. And if you think of Cartesian coordinates, x, y, and z, three are axes, that we have a dumbbell shape going around all three axes. Again, the next slide it'll be clearer. When L equals 2, we have a d orbital. Turns out there will be 5 different d orbitals, and in the right I have shown the sort of labels that we use for these. Again, it's looking a little complicated now, but wait till I show the next slide and it'll clear up a little bit. The third quantum number is called the magnetic quantum number, ML, M with subscript L, and it has values of 0, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus whatever L is. Now this again seems complicated the first time you look at it, but if L is equal to 0, then ML can only be 0. If L is 1, then ML can be minus 1, 0, or 1. Okay, and if L equals 2, if we're in a d orbital, L equals 2, we can have values of minus 2, minus 1, 0, plus 1, and plus 2. Minus 2, minus 1, 0, plus 1, 5. Yes, 5, and those correspond to the 5 different labels we have here. dxy, dxz, dyz, dz squared, dx squared minus y squared. These are just different. These are just labels for the individual orbitals characterized by magnetic quantum numbers. So basically the ML is another kind of label, an alternative label. So the dxy, dxz, dyz, etc. This is one way of labeling the individual d orbitals. Another way is by using this type of notation. That is by saying that one is the minus 2 ML value, then the other is the minus 1, then this one would be 0, the plus 1, the plus 2. Now, what you're probably thinking is, well, does it make any difference whether or not I say dxy, that label is the same as minus 2, or is it plus 2, or is it minus 1, or plus? It doesn't make that much difference. Don't worry about that. The last thing on this slide that is stated is that these individual labels actually correspond to orientation in space. Now, this probably seems confusing now, and you can back up and go through this slide again, but it probably will help a lot by just going to the next slide or two. This table kind of summarizes the possibilities. When n equals 1, we can only have a 1s orbital, and its magnetic quantum number can only be 0. When n equals 2, we can have L equals 0 or 1, meaning we can have an s orbital or a p orbital. Now notice the 2, or the 1, the 2, the 3, the 4 in front of these letters. This 1 and this 2 corresponds to the n value. So we say this is at energy level 1, this is an s orbital at energy level 1. When n equals 2, we say at this energy level 2, we have an s orbital. We can also have a p orbital. Energy level 3, we can have an s, a p, and a d. Energy level 4, we can have an S, P, D, F. Okay, it's probably starting to come into focus a little bit more. And there is only a single type of s orbital, and its magnetic quantum number is just called 0. Likewise for 2s, we just call it 0. But when we go to p's, there are 3 different p orbitals, and we can call one minus x, 0, and plus 1. That's one way of labeling them. Another way is to call one of them px, py, pz. Okay. For 3s, there's only a single type of orbital. We don't have to, label it, one different from the other. For p's, for the 3p, there's 3 types of p orbitals, minus 1, 0, plus 1. Again, this could be also called a px, py, pz. When we get to 3d, we can have a magnetic quantum numbers of minus 2, minus 1, 0, plus 1, plus 2, and we have 5 of the d orbitals. And remember those labels, dxy, dyz, dzy, etc. That's an alternative way of labeling them. Now, after saying all this and showing you all these quantum numbers, what do they look like? And I think after this slide and the next one, it'll clarify a great deal. The s orbitals are spherical orbitals. And if you look at the top part, they're just now they're not hard spheres. They actually kind of thin out from being close to the nucleus as you go out. But the only way we can sort of represent them easily is just by drawing them as a sphere. Now, what I show on the top slide is what you could call a 1s, a 2s, and a 3s orbital. That is, you have s orbitals at each of these energy levels, energy level 1, 2, 3, and then 4, 5, 6. And they all look about the same, except when you go to higher n values, the s orbitals get bigger. Okay, because the electrons are further away from the nucleus as you go to higher n values. The p orbitals, the ones that I call dumbbell in shape, have two lobes and a node. The node being at the nucleus, where the center of our Cartesian coordinate. We have a lobe that would go on the positive z-axis, and one that would go on the negative z-axis. Or this one would be the px, two lobes and a node, or the py, two lobes and a node. So we can imagine it's kind of like a figure-8 racetrack where the electrons are zooming around. Okay, so this is what the p orbitals look like. Now, if we go from energy level 2, which can have p orbitals, to 3, to 4, to 5, each of these can have p orbitals. The difference would be that as we go to a higher n value, the orbitals get further and further from the nucleus, so they get sort of larger figure-8 racetracks. All right, now the d orbitals. Are you ready? The d orbitals, we said there are 5 of them, and whoa, they are funky looking. Probably the easiest of the d orbitals to understand is dx squared minus y squared. That's just its name. Don't get hung up about it. It's just we have to call them something. This is its name. What you'll notice about a d orbital is that it has 4 lobes and a node right in the middle where the nucleus is. In dx squared minus y squared, these 4 lobes lie along the x-axis and the y-axis. Okay, the x-axis and the y-axis, that's where the 4 lobes are, and nothing along the z-axis. Okay, 3 other orbitals called dyz, dxz, and dxy also have 4 lobes and a node in the middle. But in these cases, the lobes are offset from the major axes. Now, it's a little bit hard to see in the drawing. If you look in the drawing in the book and carefully, you can see that what I'm talking about, that the lobes are offset from the major axes. The other one is called dz squared, and it is really funky looking. It has 2 lobes that go along the z-axis, and then it has a donut around the waist. We'll have examples later on throughout the course where we'll talk about the d orbitals, and we'll see that dz squared and dx squared minus y squared are the ones that we probably have to pay most attention to, because the other 3 really are kind of similar. It's just their orientation in space. So we have d orbitals. All right, now putting this together and representing it in a different way. Here's another way to draw out the energy levels. On the left, I have energy level 1. So this is the lowest energy level. Remember our Bohr energy calculations. Minus 2.18 times 10 to the minus 18th joules would be this energy level. Then we have energy level 2. Then we have energy level 3. And then energy level 4. And then energy level 5. And we could go on and on. Now, actually, these get spaced closer together as we go up, but I drew them a little bit further apart just so that you can see. For an energy level 1, we can only have L equals 0 and only one type of orbital, which we can also call 1s. See, it's starting to make a little more sense. And the ML value is only 0, so it's kind of boring. We just call it a 1s orbital. At energy level 2, we can have L equals 0 and L equal 1, corresponding to what we would call a 2s orbital and 2p orbitals, but there can be 3 of these 2p's, which we could call -1, 0, or +1, or px, py, pz. 3 different orientations in space. Okay, making some sense. For energy level 3, we can have L equals 0, we can have L equal 1, and we can have L equal 2. That is, we can have 3 s orbitals, 3 p orbitals, and 3 d orbitals. Going back to 3s, there's only one type of s, ml equals 0, one type of s. The p orbitals, there are 3 types of p, -1, 0, +1, or px, py, pz. We would call it 3px, 3py, 3pz. And for d orbitals, there are 5 possible ml values, -2, -1, 0, +1, +2. So there are 5 d orbitals, and this alternative label system would be dxy, dyz, dzy, dx x squared minus y squared, and dz squared. Different ways that we could label the 3d orbitals. And likewise, we could go on to energy level 4, and yes, at energy level 4, we can now have 4 f orbitals. We could go on to energy level 5, and we'd have the f. We would also have g's, and I just didn't draw them out here because we never get to that in chemistry. We never get past the f's orbitals. Okay, now we're going to see that the way we build atoms is by placing electrons into these possible orbitals. We'd say, where is the first electron going to go? Well, it goes into the lowest available orbital. Where is the next electron going to go? Well, and we'll talk about this. We see this arrow that I have. This would be one electron placed in the lowest energy orbital, and that would be the hydrogen atom. This would be a representation of where the electron, the orbit that the electron, the single electron of hydrogen chooses to exist in, the very lowest energy orbital, the 1s orbital. Now, if we shock it with electricity, we may make it jump up to energy level 4 or 5, and then it may go back down to energy level 3 or 2, and that's the emission spectrum that we see in the line spectrum of hydrogen gas, when it goes back down after it's been shocked up and kicked up to a higher energy level momentarily. But most of the time, it will be down in the lowest energy level, the ground state, 1s. Okay. Now, in actuality, once we go beyond the hydrogen atom, it turns out that this organization of energy levels becomes skewed. And I show in this diagram the 6 electrons for carbon. In the next set of lectures, we will explain all this, but we have 2 electrons in the 1s orbital, and I have one represented by these arrows, one arrow pointing up, one arrow pointing down. We'll explain why. Then we put the next electrons in the 2s, one pointing up, one going down. And notice that the 2p orbitals are not at the same energy level. They're slightly higher than the 2s orbitals. Likewise, for the energy level 3, I have the 3s orbital here, the 3p a little bit higher, the 3d a little higher. Then the 4s orbital, the 4p a little higher, the 4d a little higher. 5, and 4f is way up here. Then 5s, 5p, 5d would be here. I just didn't draw it. 5f, 5g up here. But what is important is that this skewing can lead to something that we'll see is very important. That is that actually the energy level of 4s can be lower than 3d. So while we may think that we first fill electrons into the energy level 1, and then energy level 2, and then energy level 3, actually what happens is that we can fill into energy level 4s before we fill into energy level 3d. And similarly, there will be some out of order ordering of the electrons in some other atoms. And we'll get that into the next chapter. So this is the end of this lecture. The next slide, we'll talk about other elements besides hydrogen and carbon, how they're formed by adding electrons into these available atomic orbitals. We'll see how this is all related to the layout of the periodic table, and we'll discuss magnetic properties. We'll introduce the concept of being paramagnetic and diamagnetic. We'll discuss how ions are formed, and we'll discuss periodic trends of the element. That's what you get to look forward to for the next video lecture. All right, see ya.